Greetings, calculus scholars. Mr. Benzel here, beginning section 4.9a notes, finding the area between the curve with respect to x. You may be wondering why we skipped 4.8. 4.8 requires a lot of graphing, and I wanted to make sure that everybody had access to graph papers and those type of features. So 4.9 kind of begins our area between two curves section of calculus. So today we're taking the area between two curves with respect to x. So the question is, how do we compute the shaded area? So one idea that people may want to think about, we could draw like geometric shapes, like maybe those rectangle thingies. But the question becomes, how do we avoid all these rectangles? Well, it turns out that there's a symbol, this integral symbol, that gives us the exact area. And maybe, just maybe, we could maybe do a combination of different integrals, like if we could add integrals or subtract integrals, and we could actually get the area under the curve. So just to kind of give you an idea about where we are going, we could be thinking about maybe the idea that this shaded area, I'm just going to show you geometrically what's going on today. So we have a shaded area. What if we took the total area of like this trapezoid, and then we subtracted it maybe by an area that we knew how to do with just a regular integral, area under the curve. Maybe that could work. And just to kind of show you what's going on, what we cut out, this shaded area. So this is geometrically what's kind of going on. We can also frame this as sort of a warm-up problem. And if you were in the brick and mortar classroom, this is where we would kind of start today's lesson at. So part A just says, let's take the integral of that top function. Compute the area under the curve. That means take the integral. And we're taking the integral of x plus 3 from -1 to +2. And when we do this is a pretty straightforward antiderivative. So x squared is a half plus 3x plus c. And we're evaluating it from -1 to +2. If we're evaluating this, you could just go to your calculator even and see what number it comes out to. Or if we're just kind of doing this one at a time, put in my 2 squared plus 3 times 2. So that gets me to a total of, 2 plus 6, which is 8. And then the -1 part would get me to 1/2 times -1 squared plus 3 times -1. So that's when we do that, we would get a 1/2 times -3. That's a minus 2.5. So we would just do 8 minus a -2.5, which gets us to 10.5. And we can kind of see here that if we look at the total area under that curve, that top curve, and I'll just do it here in red, it would be about 10.5 because, this bottom thing would get you, like this bottom rectangle, that's 6. And then you have half of 9, which is 4.5, so that would get you exactly 10.5. Now, if this were, like if we had to do a geometric area, and it was pretty clear, like it was like a trapezoid or a rectangle plus the triangle, and you saw the geometry immediately, you wouldn't even have to really do the antiderivative, and you could actually come up with 10.5, pretty intelligently. We like you knowing that the integral is the area under the curve. All right, so now let's focus on this next part. Part B says compute the area under the curve of x squared plus 1 between -1 and +2. So let's look at where this geometry is going on. We'll do this maybe in green. So we're taking this line here. And we're taking that green area. Obviously, you can't fake the geometry in that. So if we do the integral here, we're taking this from -1 to +2. And the function is x squared plus 1 dx. So when we take this integral, we get x cubed times 1/3 plus x. And we're going from 2 to -1 to 2. And there is that, plus c that's in there. And let's see, when we evaluate this, we get 1/3 times 2 cubed plus 2. That gets us to, 8/3. 8/3 is about 2.67 plus 2, so that's 4.67. And then we subtract this by 1/3 times -1 cubed, so that's a -1/3 minus 1, so that's about -1.33. So when we combine these, it's about 3 minus a -1.33. So that's about 6. And if we look at our graph here, the green area, well, we have 3 squares accounted for, and then the stuff above, is probably about 3 more squares, when we look at those half a square things. So we would get about a total of 6. So now it just says subtract your results from A and B. So if we do that, we get 10.5 minus 6 for a total of 4.5 units squared. So we just broke this down into, two area under the curve problems, and we knew how to do these individual integrals easily, and we could actually use this and come up with the, not total area because we're, not adding them, but the difference between those two areas. And let's just look at our graph and see, does 4.5 kind of make sense? And let's see, we got one rectangle, two rectangles, and then we have, just a bunch of like half a rectangles that probably add up to something around 4.5. And we didn't even have to do any like Riemann sums with that. So this is a nice introduction to finding the area between the curves. Now, we're going to go and look at a few more problems in the next video. So I hope that you join us.